is the question we're answering right now. So I'm going to take you guys from the very basics on this. Some of you who are like senior engineers, maybe you know this. Maybe you've done rocketry before, maybe you know this. We're going to start at 0, and we're going to go all the way up. Okay, we're going to cover what type of fuel is used in rocket propulsion. What is the difference between a rocket motor and a rocket engine? They are different. What does the inside of a rocket motor look like? How is a rocket motor ignited? What is a nozzle? Why is it important? And how do you describe motor performance? All right. So, like I said, we're starting at 0. Do all of you guys know Newton's third law? Have you heard this before? Yes. I love Newton's third law. Good. So, this is all you need to remember in your brain for you to understand how a rocket works. Intuitively. There's math, which we're going to brush on. But intuitively, all you need to keep in your brain is, for every action, there is an equal and opposite reaction. Let's look at an example of that. Who here has seen a problem like this in their physics class? Raise your hand. Okay, good. This is familiar to most of y'all. If you haven't seen it, don't worry, I'm about to explain it. So like I said, for every action, there's an equal and opposite reaction. Let's imagine that you're standing on an ice skater rink, you're wearing ice skates, and you have a big, heavy bowling ball in your hands. And what you're going to do is you're going to throw it off of your chest. Can someone tell me what happens? Describe what happens when you do that.
You go the other way.
You go the other way. The ice skater. Yes. So the bowling ball goes forward, but you also go backwards. Well, if I did that right here, if I threw a bowling ball, I wouldn't go anywhere, right? Why? Friction. Yeah, so there's a friction on my feet holding me in place. But there's nothing for that for our ice skater friend, so he feels that equal and opposite reaction back on him. Okay? Remember the bowling ball? Now let's apply this to a rocket. All that gas and smoke coming out of the back of the rocket, that's the bowling ball. That rocket is just throwing mass out of the back of it at an extreme speed and an extreme amount of mass to reach space in this example. So you can think the rocket motor is just a fancy mass-eating machine. That is all it does. It squeezes as much mass as fast as possible out of the back of it, and it launches itself into the atmosphere. That's how a rocket motor works. And, well, the reason you get all that mass coming out the back is because of explosions and stuff, but that's the main part of it. That's why you can build a water bottle rocket, right? All that water coming out of the back is your mass leaving your object. Is everyone clear on that intuitive understanding? Any questions, confusions, or concerns at this point? Please yell them out. Okay. Now we're going to go to math. So I'm not going to go through all this. You can read this on your own time if you're a freak. But it's pretty cool. So if you break it down, it's actually related a lot to momentum. So in this first example, I give you a case where mass is ejected at a constant velocity. So you see that V right there is constant, and it's just a derivative of the change in mass over the change in time. In a real scenario, both mass and velocity quantities are changing throughout the whole thing, so the math is a little bit more complicated on that, and so you can see down here how that breaks down through the conservation of momentum rules. I was a physics major, so I used to do this, but I'm graduated now, so I'm not gonna do it. Okay, so this goes through all of it. I pulled this from a website if you want to go there, and they have more words. But your end result is you get an equation where the change in velocity is on your left-hand side. So this big one right here. And on the right side, it's related to your ejection mass speed, which is U. That was a terrible drawing. U. And your initial mass over your rate of mass leaving. Yeah, I can't draw this. So this was first come up with in 1897 by Konstantin Tsiolkovsky. He is considered the father of rocketry, and there is a picture of him on board the Russian segment of the ISS at all times, because the Russians love him. Okay. Types of mass-eating machines, aka rocket propulsion. So there's two types, motors and engines. What's the difference? So a motor, at least, so this is not related to cars or motorcycles. When you think of a motor in those terms, it's not related to this, but when we're talking about rockets, a motor has fuel that is in the solid form only. So the thing you're burning inside of there is solid. Versus an engine, at least part of the fuel is a liquid or a gas. Another difference is in a motor, once the motor is lit, the burn cannot be controlled. On an engine, the burn rate is controlled by the speed at which gas is injected into the system. In this camp, we're only going to focus on motors. Why? Well, our team, like I said, we did commercial off-the-shelf motors. We have only ever used motors. We've never actually used an engine on this team. So we would love to do that in the future. I think we've all talked about doing an SCR motor or an SCR engine. It's on the horizon, I'm sure, but it's too much to cover in this conversation today, so I'm going to skip it. Okay, parts of a rocket motor. Any questions? Any questions? Okay. Parts of a rocket motor. So I actually have one right here to show you. This was the rocket motor used on Zenith. It's pretty big. This is an O-class motor. And right now it might not be obvious if you didn't know what this object was that it was a rocket motor, because it just kind of looks like a big cylinder, right? Well, if I cut this in half directly like this is what would be on the inside, if it was full, which I don't think it is. It's not full, right? You're not giving me live explosives in here, are you? Joe and Robbie? Alright, whatever, who knows? Alright, so if you cut that in half, cross-section, what's inside of there? Well, where's my freaking laser point? So on the edge here, this part right here, this is your metal casing. This is your cylinder. And if you looked inside, you would see that they've got these areas right here that is all propellant. So this pinkish area, this is your propellant. This is the thing that's going to burn when you light the motor. How do we light the motor? Well, we have a little thing back here called the igniter. This is placed at the very tip of the motor away from the exit area. So this is where all your gas and smoke is going to come out of. It's placed at the opposite end. And then down here, right here, that I alluded to, this is the nozzle. This is where all your gas and mass is going to be ejected from. Okay. I hate that this does not erase itself. I wonder how you do that. Okay. So how do you get it to start burning? You have this nice, lovely case. You have it full of explosives. How do you get it to start burning? So when you're ready to launch and everything's standing up on the launch pad and you're, 3, 2, 1, go. You set off a tiny little charge on the igniter. So this is electrically controlled. There's just like a little fuse in there. So when you run a current through it, it generates heat across these little wires. That is in contact with a small amount of really explosives, usually like gunpowder. And this is trying to create like a little flame, a little pop inside the back of your motor. This is going to set the surrounding propellant on fire, and that propellant is going to start generating gas. And that gas is going to travel away from the heat source towards the back of the motor. Oh, something I didn't cover. This little part in the middle is hollow. I'm not sure if y'all picked up on that. That's how the gas can travel from here all the way over here. And that little part in the middle, does anyone know what that's called? That hollow area? Advanced rocketry people? Anyone know?
Combustion chamber?
No.
No.
That would be in an engine. We're not talking about an engine. It's called a grain. Weird word. That hollow bit in the middle is called a grain. Okay. So in our last slide, we saw the gas was traveling down towards the nozzle. Why is the nozzle there? What does the nozzle do? Well, I'm going to give you guys an example. I was thinking about this as I was making this slide. When you were a kid, did you ever play in the backyard and you had the garden hose and your brother is running around being a goofball and you want to squirt him with the garden hose, but it's slow and it's just falling out? So you put your thumb over it so it goes farther and faster so you can hit your brother and tease him and he's screaming, "Everyone, stop squirting me with the hose! Mom!" Okay, same concept is going on here in our rocket. We're squeezing the tip so that it compresses all the gas and it goes out way faster than if we just left it all open. So that works to a certain extent, right? But if you also think back to your hose example, there's a certain point where you can't really get it to go any farther, right? You've reached the limit. You can keep making it tighter, but it's really only going to go so far. What that means when that happens is that you kind of hit the limit and you've choked your nozzle, or in this case, your garden hose. You've choked it. It's related to compressible fluids, which there are certain topics in these presentations I'm going to admit I don't know, I'm not an expert on. So I've done all sorts of rocketry, but I was not trained as an engineer. I was trained as a physicist. So if you want to talk about the speed of light, I can talk to you. I cannot talk to you about compressible fluids. So we're going to watch a video that explains that. Basically, what I'm trying to say is to overcome that choke, you're going to have to open the motor back up, and it's related to how compressible and non-compressible fluids work.
Hello, fellow armchair astronauts, and welcome to part 3 in our series on rocket engines. In this part, we're talking about the converging diverging nozzle. Before we start, I'm going to give a quick disclaimer. This episode touches on the subject of fluid dynamics, which is a pretty complex field of physics. In order to keep this video short, relatively free of math, and friendly to a broad audience, I will make a few grossly oversimplified explanations of how some things work. So take what I say with a bit of salt, and with that out of the way, let's cue the intro.
All right, lift off and the clock is started. Lift off. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Discovery, go throttle.
The converging diverging nozzle is the most common type used in rocketry, and it works by converting pressure energy from the fuel flow and heat energy from the combustion of fuel into kinetic energy in the form of high exhaust velocity. There are 3 sections of the converging diverging nozzle. The converging section, which starts at the combustion chamber and gets more narrow, the throat, which is the most narrow part of the nozzle, and the diverging section, which starts from the throat and expands to the nozzle exit. To understand how this nozzle works, you first need a quick crash course in fluid dynamics. Flow rate through a pipe is constant for incompressible flows. The amount of fluid moving through any section of the pipe is always the same, even if the size or shape of the pipe changes. Flow rate is equal to the velocity of the fluid multiplied by the cross-sectional area of the pipe. So if the cross-section becomes smaller, then the velocity of the fluid must increase for the flow rate to stay the same. Usually, liquids and gases traveling at low speeds fall into the category of incompressible flow. However, if a gas is traveling at or above its local speed of sound, it will become a compressible flow. Compressible flows behave a bit differently. Flow rate is no longer tied to pipe cross-section, since the density of a compressible fluid can change. This means for a gas flowing at speeds above Mach 1, velocity can actually increase as pipe cross-section increases. Conservation of energy is an important part of this as well. The increase in kinetic energy as flow velocity increases means some other form of energy must decrease. In this case, that energy is coming from the heat and pressure of the fluid. That is to say, as velocity increases, temperature and pressure will both decrease. In the converging section of a rocket nozzle, the exhaust is traveling at relatively low speeds from the combustion chamber, so it is pretty much an incompressible flow. This means that as the nozzle gets more restricted, the velocity will increase until it reaches the local speed of sound. In a rocket engine, the local speed of sound is going to be much higher than the speed of sound in Earth's atmosphere. This is because the speed of sound increases with temperature, and a rocket engine is very hot.
Okay, we're gonna stop there. Anyone have questions? I will attempt to answer them. Okay. So, related to when a fluid becomes compressible or incompressible, how it relates to the speed of sound in a fluid. Long story short, if you open it back up again and it's the right temperature and speed, it works. It works. You can go supersonic. You can get over that choke. Oh, not Okay. So now, that's pretty much everything that's happening in here. This is like a terrible picture, but this whole compartment, the grain, is going to fill up with gas. It's going to be super pressurized, flowing out of the back of the nozzle, and this is where all your mass comes out of, sending your rocket up. So now we know how a rocket goes up. Woo! Okay. So that's pretty much the last of the physics and engineering. Now we're just going to talk about kind of how we describe motors in the rocketry community. So motors have scales. So the least powerful motor you can buy is an A-class motor. It's the little guy down here. And the most powerful motor you can buy, well, it's not a Z, but that would be the logical conclusion. It's more like an O-ish. It's a little higher than an O, right? I don't know. Like a T or something like that. If you go higher than T, you're basically getting into military-grade rocket motors, and civilians cannot buy those. Although the NASA and everyone has certainly made things of that type before. But this works on a log 2 scale. So basing off of our first class A, on the left-hand side we have total impulse. So impulse is analogous to the thrust generated by your motor. And you can see that our A-class motor has a total impulse of 2.5 Newton seconds. Moving up a class to class B, we can see its max it can have is 5 Newton seconds. Moving up a class, we see C can have up to 10, D can have up to 20. What's the pattern here? What are we doing as we move up? Can someone answer? It's doubling. That's what a log 2 scale is. Log 2 scale means that each category is doubling. Cool, easy. What about this E right here? So this is labeled E. Is that correct? Is this still an E-class motor, this one on the right-hand side, even though it doesn't go all the way up to 40? It is. I see some nods. Why? Someone tell me why. Yes, it is higher than D. It's higher than D, which is here. And it's lower than the peak of E, right? So 40 Newton seconds is the peak that an E-class motor can have while still being called an E-class motor. If it goes to 41, it's now an F-class motor. So it can have anything in this range right here. Clear on that? Erase all my marks. Okay. All right, so here's a chart kind of describing a few different rocket motors you might be familiar with and what class they fall into. So water bottle rockets, if you've ever built one in your backyard, that goes up to a D class. We're going to get into kind of what is a level 1, level 2, and level 3 cert rocket later. But if you kind of know those concepts already, you can see what a level 1 usually goes up to H class. If you don't know what level 1 is, actually, I'll probably just go into that right now. So I have this rocket here. This is a Killer Carrot. This is my L1 cert rocket. Basically what that means is there's an organization around here called Tripoli. They are a hobbyist rocketry group, and you can get certified to launch bigger and bigger rockets through them. So basically you build your level 1, which is a small little rocket, prove that you can successfully launch that and follow all the procedures. Then after that, you're allowed to buy higher, more powerful motors. So after that, you're allowed to go from H all the way up to J-ish. Level 2, if you want to go past J, you have to get your level 2 cert. Bigger rocket, more complicated rocket, more requirements. After you've done that, you can go up to your LM class, get your level 3 cert. That's the highest cert you can get, and you're now cleared to buy any rocket motor you want. However, like I said, civilians can only buy up to, T, I was right. FAA definition of an amateur rocket. After that, your military stuff. So you can see some famous rockets and what class they would fall into. They don't really follow this scale that I've described, so this is like a hobbyist scale, this Log 2 scale. They would not classify like this, but this is just an analog to see what are those rockets' power scale in comparison to something like this. And so I haven't even included, remember, AG was the most powerful rocket ever launched. That was a Saturn V. I clipped that. But like our Falcon 9, right here, that's an AE. It's pretty high up there. All right, and let's take a step back, something I forgot to cover. The grain. So what was the grain? Someone remind me what that was.
The gas chamber.
Yeah, it's the chamber in the middle of your rocket motor that's like a hole. Well, spoiler alert, it doesn't have to be a hole. It can be all types of shapes, and here's an example of some we have. So this hole in the middle one, we've been describing this, is called a Bates grain. This is your most standard rocket motor grain. Really, you're not really going to be able to use any of these unless you make your own motor and you're like, hey, I want to use a double anchor. Most standard commercial off-the-shelf motors are going to use this Bates grain. Something curious about these you can see as well, though, is that different grains give us different characteristics. So you can see each of them has a little graph. This is the thrust and this is the time. So this is describing once you light your rocket, how is it going to behave as it flies through the air. It's not just like, you light it and it's a constant thrust out the back. It changes. It's very dynamic depending on how you set up your grain and what propellant you even use. This is hinting to our next topic too, that I want to cover. The thrust curve. So this in detail tells us every characteristic about a rocket. Or sorry, not a rocket, a rocket motor. So the class tells us how powerful it is. This tells us how it behaves over time. So let's say your mission requirement is you want a rocket that's going to burn very stably for a long time. You want a constant long burn. You want something more like this, where the thrust is constant most of the flight. What about instead you want to reach the highest speed possible? Not our goal here, but let's say that was your goal. You might want to use something like this, where it peaks really high and then goes down. Notice the time scale here too. This stops burning at 3 seconds. Oh, sorry. This stops burning at 3 seconds. This stops burning at 1 second, right? So you also need to take a look at how long is your motor going to burn and output that thrust anyway. There's a lovely website for any rocket motor you pick out. You can look it up on thrustcurve.org. It's going to give you this. So people in the rocketry community have tested these motors on something called test stands that measure the thrust over time, characterized their performance, and published it, which is really helpful. Okay, how do we name a motor? So you may have noticed on the last slide, I put the names of the motors down here. These are kind of weird. What does that mean? Well, there's actually a very standardized system to name a motor. So right here, I put an example of a small little E-class motor, an Aerotech E28-4T. Why is it called that? So Aerotech, that is the name of the manufacturer. E tells us that it's an E-class motor. 28, this tells us the average thrust in Newton seconds of the motor while burning. So this is slightly different than your peak thrust. This is the average. So if they drew a line through all of the points on that thrust curve we talked about, right? That's your average thrust. 4 is how many seconds after ignition that the ejection charge will go off. This is not used in motors above L2. So this goes into a recovery system that's really not applicable to our type of rocket. But if you do your L2 or your L1, you're going to want to know about this. Only applies to little motors. So once we get into the big M-class motors, you don't need to worry about that. And then our last part, T, this tells us the propellant type. In this case, it is the Blue Thunder propellant from Aerotech. You won't know that just by looking at it. You've got to look that up on the website. But they'll have a key there that says if your motor says T, that is Blue Thunder. So we're going to practice. Get my pen. All right, who can tell me what is the manufacturer of the Cesaroni P38-1G? Cesaroni, woo! Okay, good. We're learning stuff. What class motor is it? P. Good. What is the average thrust of this motor? 38 what? Newton seconds. Good. All right, what is the ejection charge delay on this motor? 1 second. Perfect. And lastly, what is the propellant type? G. So we don't know what G means until we look it up on the Cesaroni website, which I've done. That is their green propellant. So we got that perfect. Good job, you guys. Let's do a harder one. What's the name of the manufacturer? Loki. What's the motor class? M. What is the average thrust? 3,000 Newton seconds. That's a lot bigger than our previous one. Gee, we went from 38 to 3,000.
That's not low key.
Not low key at all, you're right. All right, what's the ejection charge delay on this? There is not one. Good. So it's not L. Good guess though. It's an M-class motor. It doesn't have an ejection charge. There's no number. 0. And what is the propellant type then? LW. All right. So looking that up, LW is Loki White. We got everything correct there. Oh, and guess what? That's the motor we use on Oberon.